All right, now, wonderful day out, and it looks like it's time to do some calculus. So here's the do now, pause it if you need to, and then you can pick that up now. I will point out that here, sequences, last section, down here, you're going to have to do long division for that one. So yeah, I know you guys all love long division. Answers, yeah. There we go. That was the assignment from last time. It is on your on my website, not your website. So feel free to access that. Okay, so here we have Power Series, Section 9.1. I will give you a heads up. This is one of my favorite sections. A lot of cool stuff goes in here. So let's start it off with a wonderful, wonderful joke. An infinite line of mathematicians walks into a soda shop. The first mathematician says, "I'll have half a soda." Second mathematician says, "I'll have a quarter of a soda." Third says, "I'll have 1/8 of a soda." The fourth says, "I'll have 1/16 of a soda." The waiter at this point grows impatient and says, "Enough!" and puts one soda on the counter. Then the mathematicians say, "Hey, what's your problem?" The waiter replies, "Know your limits." Okay, so we all know what makes a joke funnier, and that is to explain it. Am I right? Am I right? Am I right? Of course I'm right. So here's how it works. You get 1/2 plus 1/4 plus 1/8 plus 1/16. Hopefully you guys can actually see the pattern here. What I'm doing is I'm doubling the denominator or multiplying by 1/2 each and every time. And what you can actually see is that sums to 1. Looking over here, here's a nice little representation of it. We have this square right here, which is just the unit square, 1 by 1. You take half of that unit square, and then add half of that half to it. You get 1/4. Half of that 1/4 is 1/8. So we just keep filling in that half as we spiral in toward the infinite terms here. So if I was able to add infinite terms together here, I would actually produce an infinite series that sums to 1. So a couple of vocab words that we have here. Infinite series. Infinite series is just adding a bunch of numbers together. Converges means it gets to one number. Because we have one number, it converges to 1. Now, there are series out there that do not converge. Obviously, like 1 plus 2 plus 3 plus 4 plus 5, that does not converge. This is another series that does not converge. This is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, blah, 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 blah. That actually ends up being infinity. So here's technical definition for an infinite series. An infinite series is an expression of the form a1 plus a2 plus a3 plus blah, 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 all the way to a sub n. Or you hopefully remember sigma notation from quite a while ago. Sigma notation is just the summation from k equals 1 to infinity. The number down here is where we start. The number up top is where we finish. And a sub k. So there is a way that you can write an infinite series if you can actually figure out the kth term on there. The numbers a1, a2 are the etc., etc., etc. are the terms of the series, and a sub n is the nth term. Don't worry, we're going to be doing a lot of stuff with that today. So here, you got what are called partial sums. Partial sums. Something that I kind of glossed over here. An infinite series is you just take the sequences from last class and you add all the terms together. So here, partial sums. A partial sum itself, or you can make a sequence of partial sums. And partial sums are just take the first number. Your second partial sum is add together the two numbers. Third partial sums would be add together the first three numbers. The nth term is going to be the summation from k equals 1 to n of a sub k. If the sequence of partial sums has a limit s as n approaches infinity, we say the sum series converges to the sum s, and we write a plus a1 plus a2 plus a3 plus blah blah blah, or the summation from k equals 1 to infinity of a sub k is equal to s. Otherwise, we say the series diverges. So if you get one singular number, converges, not a singular number, it diverges. And sometimes we have series that diverge slowly, so it's actually kind of difficult to do this. If we look back at our series from over here, we can actually get the partial sums off of this. So the partial sums on this, let's get up here. So S1 is going to be 1/2. It's just the first number. S2 is going to be 1/2 plus 1/4. So it would be, let's see, 3/4. Am I right? I think I'm right. Plus 1/8. S3 would be equal to, let's see, 3/4 plus 1/8. So that would be 6/8 plus 1/8, 7/8. If we want to write this a little bit more succinctly, we could have S sub n is equal to 1/2, 3/4, 7/8. And sometimes you do actually have to go on quite a bit in order to figure out what the nth term is here. If we were able to go on forever and ever, we would eventually find out that it becomes 1. So partial sums, if you get one number, converges. If you don't, diverges. So let's look over here. Partial sums to decide if these series converge. So I want to put this in a much more succinct fashion. So I'm just going to skip right to that S sub n. And that S sub n, I look at the first term. First term is just 2, right? So the first partial sum is 2. Second partial sum is, just go for the first 2 terms. 2 minus 2, 0. Third partial sum, 2 minus 2 plus 2. Okay, so 2. Fourth partial sum, okay, 0. 2. Can we see the pattern here? Is this going to one singular number? The answer is no. I know you guys can't respond to me, but since it doesn't go to one singular number, this sum oscillates back and forth between 2 and 0. We say that the series diverges. I will point out that this is a really bad way to determine convergence or divergence, because technically you have to go to the nth term, which is infinity, and that's going to take a long time. So it only works, some of the time to do the partial sums to determine divergence or convergence. Don't worry, we're not going to give you really difficult ones to do using the partial sums. But I look at this. I know that, well, 7/10, that's just 0.7, right? So the first partial sum is going to be 7/10, or 0.7. 7/100 is 0.07, so this becomes 0.7 plus 0.07, 0.77. 7,000 becomes, let's see, 0.007 plus 0.77 becomes 0.777. Can we see what the pattern is here? It looks like each and every time I'm just shifting that 7 for the term over one more decimal place. So it looks like this would be 7s throughout, or 0.7 repeating is what we would call it. Yeah, cool. Again, using partial sums, I guess we should probably answer the question. Converges. And whenever you say that a series converges, if possible, you like to say what it converges to, and we're just going to say it converges to 0.7 repeating. Look over here for the answers. Again, using partial sums, bad way to do it, but sometimes it's all you have left for this one. But wait, I hate decimals. Can I rewrite 0.7 repeating as a fraction? Oh, yeah, hey, cool. I think I can. I don't know what it is. If you know it, don't tell me. So here, what I actually have to do is, in order to answer that question, I'm going to try to do some long division on this problem. So I can actually see I've got 6 divided by 1 minus x. And again, we all remember exactly how to do long division. Divide, so 6 divided by 1, I get 6. Multiply, I get 6 times 1 minus x, I get 6 minus 6x. Subtract, so switch the signs, and add down, I get 6x. Okay, nothing to drop down, so I'm just going to do the divide step again. Okay, this looks like it's going to get fun. 6x divided by 1 gives me plus 6x. 6x times 1 minus x becomes 6x minus 6x squared. Subtract. Oh, it looks like 6x squared. Okay, so now I've got 6x squared divided by 1, I get plus 6x squared. Multiply, I get 6x squared minus 6x cubed. Oh my gosh, can we see a pattern here? It looks like the next time, or the next term that I'm going to have here is plus 6x cubed. Looking up here, I can now see the pattern. It looks like all I'm doing here is adding 1 to my exponent each time. So the next one would be 6x to the 4th, 6x to the 5th, etc., etc., etc. So the nth term is going to be 6x to the nth. I can actually say that this can be represented as a polynomial of the summation from n equals 0 up to infinity of 6x to the nth. That's really cool. And if I look right over here, I've actually drawn the function 6 over 1 minus x, and I've drawn the 35th partial sum to this function right here. And if you look on my flip chart, you can probably see it a little bit better. So it actually looks like, look at right there. It models that function exactly. I mean, outside of here, it really starts to not be quite good, but inside there, it models it exactly right. So, I swear at some point we will get back to what 0.7 repeating is as a fraction, but before we get there, I have to tell you guys something. If the infinite series converges, then the limit is going to be equal to 0. This actually gives you your first really good test for, not for convergence, but it is a test for divergence. So if the limit is not equal to 0, like the nth term is not 0, that means you're going to be adding stuff on. So if the limit as k approaches infinity of the kth term is not 0, the series diverges. So that's a really good test for divergence. It is not a test for convergence, because sometimes you can have the limit of the kth term is going to be 0, but the function does still diverge. So it's a test for divergence, but it's not a test for convergence. Okay, back to this. This is really cool. This is one of my favorite tricks in math ever. So I look at this as a divided by 1 minus r. All right? Now I do the division. I do the first term. A divided by 1. I get a. I do the multiplication. I get a minus ar. That's an r, not an n. I do the subtraction. I get ar. I repeat, ar divided by 1 gives me plus ar. ar times 1 gives me ar, minus ar times r gives me ar squared. Subtract, I get ar squared. I divide ar squared by 1, I get plus ar squared. Multiply, I get ar squared minus ar cubed. Subtract, I get ar cubed. Divide, I get plus ar cubed. So now I look up here and I look to see if there's a pattern, because at this point I'm just tired of doing the long division. But I see in each term I have the a, and the r just increases by an exponent. The exponent increases by 1 in each term. So the next term is going to be ar to the 4th. And I could check that using the long division, but I don't really feel like it. So when I get out to the nth term, I'm going to have a r to the nth power. So a over 1 minus r is actually equal to a polynomial of, let's see, the summation from n equals, and I'm going to come back and plug in what the n equals where it starts from, because you can actually start it at any number. It's really just to match our terms up here. But it goes up to infinity of ar to the nth. And now to find out where it starts, the initial index here, I look at what power would give me a for my first term, and that would be if r was a non-issue, so n equals 0, which is just really cool. That actually introduces something. Notice how here we're actually just multiplying each term by the factor r. This is extremely related to what we did in the last lesson. This is called a geometric series instead of a geometric sequence, which we had last class, or last video. This is called a geometric series, and that geometric series is a plus ar squared plus ar cubed, etc., 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 all the way ar to the n minus 1 is equal to the summation from n equals 1 to infinity of ar to the n minus 1. And just to point out here, in the stuff that I just wrote down, I started it at 0 and had the expression as ar to the n. Notice how this is exactly the same. Start at 1, so now my first exponent is still going to be 0 on that one. So it converges to the sum a over 1 minus r. That's that formula that I had on that last slide. That's an important thing to memorize. Know this. AP always asks with something about a geometric series. It sums to this if and only if the magnitude of r is less than 1. So r has to be in between -1 and 1. There's another way to write that inequality. That's just given. If r is greater than or equal to 1, or if the magnitude of r is greater than or equal to 1, then the series diverges. And this is something called an interval of convergence. It's your first experience with an interval of convergence, although it did come up over here. So actually look in here, your r is x. So between -1 and 1, we have really good modeling of, you guys don't know what this is called, it's called power series. Yeah, in between -1 and 1, good. Outside, bad. We'll be talking about intervals of convergence like a lot this chapter, so don't worry if that's too squirrely right now. All right, now let's look at these. In order to evaluate divergence or convergence on these problems, all you have to do is recognize that they are indeed geometric series. So look in here, I know that it has to be into the format of a times a common ratio to the index power. So looking here, I can see the index is n. So looking here, it looks like my r is 1/2. So the magnitude of r is going to be equal to the magnitude of 1/2. Really quick test for convergence here. Is the magnitude of 1/2 less than 1? Yes, it is. It is. It's 1/2, which is less than 1. So here I can actually find out, since if I plug in 1 here, this becomes 0, and my first term in this series would be 5 times 1 would be 5. So therefore, I can see that this series converges to a over 1 minus r. 5 over 1 minus 1/2. 1 minus 1/2 is 1/2, so I got 5 divided by 1/2, which is equal to 5 times 2, 10. Boom. This series converges to 10. So I will point out that this test, as long as your series is geometric, you can determine if the series converges. So looking over here, I've got 2/3 to the kth power, right? Oh, wait. Pause here and try to do the second one, and then pick back up now. So here I've got this number to the kth power. That means magnitude of r is equal to the magnitude of this base right here. That's 2/3. Magnitude of 2/3 is 2/3. Less than 1? Yeah, cool. So it converges. This is going to converge to, well, let's see, a is equal to the first term. So I plug in this 0. I get 2/3 to the 0 power. That's 1 times nothing. Gives me 1. So this series is going to converge to a over 1 minus r. 1 over 1/3. Converges to 3. Right? It is also a test for divergence. Looking over here, I can see I've got 2/3. Second term, 2 pi over 9. 2 pi squared over 27. Pause if you want to try this out real quick. And we pick back up now. Magnitude of r is equal to the magnitude of whatever the dang is being multiplied each term here. So I can see up here, my numerator is being multiplied by pi. My denominator is being multiplied by 3. Pi over 3, I don't want to get a calculator for this one, but I know pi is 3.1415 blah, 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 blah. Divided by 3 is greater than 1. Therefore, this series diverges. Done. I'm going to use this paper for a little bit of work here. 0.7 repeating, right? So I know 0.7 repeating is 0.77777, etc., right? I can break that apart into 0.7 plus 0.07 plus 0.007 plus 0.0007. I can keep doing that, but it's getting kind of annoying for me at this point. So what I look at here is this is going to be 0.7 plus, well, 0.07 is really just 0.07, I meant 0.7 times 0.1, right? If I multiply by 0.1 again, I'm going to get 0.007. So this would be 0.7 times 0.1 squared plus 0.7 times 0.1 cubed. Well, my goodness, this ends up being a geometric series because I'm just multiplying by 0.1 for each term here, right? So I can see here my common ratio is going to be 0.1. My first term is going to be equal to 7. Oh, sorry, 0.7. Therefore, 0.7 repeating is going to be 0.7 divided by 1 minus 0.1, which is 0.7 divided by 0.9. Multiply by 10 over 10, I get 7/9. That decimal, that repeated decimal, can now be converted into a fraction. Cool, huh? Try it out on these two, or these three. You can see I've got 0.3 repeating, 0.6 repeating. You know those are 1/3 and 2/3, right? And then we've actually got 0.9 repeating. Another party trick math, party trick math for you guys. 0.9 repeating, that's not equal to 1, is it? Well, actually it is. Because 0.3 repeating is equal to 1/3. 0.6 repeating equal to 2/3. What's 1/3 plus 2/3? It's 1. Also known as 0.9 repeating. Which is just really cool to see in the math. Here's all the math for you guys. It's on my flip chart. You can look at it. But yeah, 0.9 repeating is dead on equal to 1. Yeah, that's pretty cool. That is pretty darn cool. Alright, cool. There's your first, what we call a power series here. So this power series, actually that's the next thing up here. If the magnitude of x is less than 1 and we let r equal x, we can actually get our first series, our first power series of 1 plus x squared plus x cubed equal to 1 over 1 minus x. So this is something that you will probably want to memorize. It's something that comes up a lot. Summation from n equals something to infinity of just x to the nth power. And looking here, I could make that equal to 0 here. So that is a series that you should memorize. You could also write it as summation from n equals 1 to infinity of x to the n minus 1. Those are equivalent. Now for what a power series is. A power series is just a series like you just saw that has x's on each term. So that 1 plus x squared is just a polynomial, an infinite polynomial, if you will. We have 2 here. We have one that is centered at 0. We have one that is centered at at A. Those are both power series that you're going to have to work with here. Coefficients C0, C1, C2, C3, blah, 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 is going to be, they're just constants there. Center A is also a constant. First series would be centered at the origin. Okay, yeah. This is the same thing. It's just centered at 0 for that first one. Right, cool. Once we have a series that we know, we can find a new series by doing the same thing on the left and the right hand side of the equations. So we've got, let's see, 1 over 1 plus x, and we've got x over 1 plus x. So looking over here, part A, I can rewrite that in terms of a over 1 minus r, right? In this case, my a is going to be equal to 1. My r is going to be equal to negative x. As long as I know that, I can use the geometric series formula that I had from a couple of slides ago, right here. I can just plug it in. This is going to be equal to, that 1 over 1 plus x is going to be equal to, well, a1 plus ar, so 1 times negative x, 1 times negative x, plus 1 times negative x squared, plus 1 times negative x cubed, etc., etc., etc. So it looks like we'd have negative 1 times negative x to the nth. Well, looking at that, that's going to be 1 minus x. Square the negative, you get plus x squared. Cube the negative, you get minus x cubed. This introduces what we call an alternating series, because we go positive, negative, positive, negative, positive, negative, blah, blah, blah. One of the ways that we like to do or write down our alternating series, we just put negative 1 to the nth power here because of that nature of exponents, where evens keep this make this positive, odds make this negative. X to the nth. So I can write this as the summation from n equals something. We're going to fill in the initial index later, to infinity of negative 1 to the nth, x to the nth. And now I just go and fuzz it in what n is going to give me a first number of 1. Well, if I plug in 0 here, that becomes positive, and that becomes 1. All right, cool. N equals 0 to infinity. And I can see my interval of convergence according to the, this right here. As long as r, the magnitude of r, is less than 1, we good. So, magnitude of r, magnitude of negative x, less than 1. Well, that just means negative 1 less than x, less than 1. Yeah, cool. Okay, B is going to be a little bit harder. Wait, maybe it will be. Because I look at this, and I can write this just as x times 1 over 1 plus x, right? Let's box this in so I get some room to do this. Well, I know that 1 over 1 plus x is just going to be this 1 minus x plus x squared minus x cubed, blah-de-de, blah-de-blah-de. I just did it right here. So this, that x over 1 plus x is going to be equal to x times the quantity of 1 minus x plus x squared minus x cubed plus, forgot the ellipsis. That's not there. Dot, 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 plus negative 1 to the nth, x to the nth, blah, blah, blah. Well, I can just do a really long distribution problem. This becomes x minus x squared plus x cubed minus x to the fourth, blah, blah, blah. And just using my very rudimentary knowledge of exponents here, if I do x times x to the n, that's x to the 1 times x to the n, that becomes x to the n plus 1. Or, simply put, summation from n equals something, and I just take my nth term here to infinity of negative 1 to the nth, x to the n plus 1, and I just find something that makes the first term equal to x. Plugging in 0 works. Alright, cool. And guess what? Interval of convergence is the same as the parent. Negative 1 less than x less than 1. There we go. That's playing with a power series to get a new power series. That also comes up on the AP test, so you're probably going to want to know how to do that. There's the work a little bit more succinctly. Okay, we have this. We know that we've got 1 over 1 minus x is equal to 1 plus x squared plus x cubed, blah-de-de, blah-de, blah-de. We want to find 1 over 1 minus x squared. Okay, well, I know that this is equal to 1 over 1 minus x squared, right? This is not how you want to do this. This is a bad way of doing this, because now all I have to do is square this polynomial, right? Good news, all we have to do is really big polynomial multiplication. So a really, really big extended FOIL problem. Don't want to do that. Instead, what I look at here is I find the derivative of 1 over 1 minus x. And I will be honest with you, the only way that I know that this works out is because I have practiced it a lot. So I look at the derivative of 1 minus x to the negative first is equal to, let's see, negative 1 minus x to the negative second times the chain of negative 1. Well, golly gee willikers, I've got 1 over 1 minus x squared. What I've just shown you guys is the derivative of this guy right here is this bad boy right here. So in order to find this right here, since I know that this is equal to the derivative of this, 1 over 1 minus x squared is just going to be equal to the derivative of, and this sounds like I'm doing a lot here, 1 plus x squared plus x cubed plus, let's just put it down here, x to the nth power plus etc. Yeah, it looks like a really long derivative to do, doesn't it? Except when I realize I'm taking the derivative of 1, 0, plus the derivative of x, 1, plus the derivative of x squared, 2x, plus the derivative of x cubed, 3x squared. I really hope I wasn't going too fast there, because you're just doing power rule n times. And really here, power rule, I just put it in rule format, nx to the n minus 1. And now I can just slap it into summation form. N equals something to infinity of n x to the n minus 1. What I want to make sure of is the first non-zero term is going to be 1. So if I plugged in, I could start at 1, couldn't I? I could start at 0 where it would have 0, but I really don't even care if I put that. I can just start at 1. It's going to give me the same thing whether I start at 0 or 1. My interval of convergence is going to be the same as the interval of convergence here. I gave you the interval of convergence of that already. It's negative 1 less than x less than 1. All right. I will give you a heads up if you have to do this process, which I don't know what the name of it is. You will be told that you have to do the term-by-term differentiation, and that's what it's called. I was being sarcastic when I told you guys I didn't know what it was called. It's called term-by-term differentiation because you just differentiate each term and then go on. You do it term by term. So if you recognize that a function is equal to the derivative of a function for which you know the power series, you can do term-by-term differentiation to get the end part there. Okay. Last one. Finding power series to represent ln of 1 plus x. Well, I happen to know for a fact that if I take the integral from, well, let's just say from 0 to x of 1 over 1 plus t dt, it's just saying take the integral of this, I'm going to get the natural log of the absolute value of 1 plus t, 1 plus x rather. Okay, that's what I'm looking for, isn't it? So when I look at this, in order to find the series that represents ln of 1 plus x, it's just going to be the integral from 0 to x, and we're not really going to concern ourselves with that lower limit or the upper limit. This is just to make sure to please the mathematical overseers or whatever. Just using the series that we had come up with earlier here. T to the n with a dt at the end there. And really here, all I have to do is do the term by term integration on this one. So the antiderivative of 1 is going to be t minus t squared over 2 plus t cubed over 3 minus t to the 4th over 4, etc., 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 plus negative 1 to the nth t to the n plus 1 over n plus 1. And technically, since this is a definite integral, I've got to go from 0 to x. The 0 is a non-issue because all of these terms ends up being 0. This just ends up being x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, negative 1 to the nth x to the n plus 1 over n plus 1. And to be honest with you guys, you don't have to write out this step if you don't want to. I would be alright with you just calling it an indefinite integral. Basically, this is just me showing you why c doesn't matter in this indefinite integral. And here, it's going to be the summation from n equals something up to infinity of negative 1 to the nth x to the n plus 1 over n plus 1. And to make the first term into just x, it looks like if I plug in 0, that's going to work. Interval of convergence is going to be the same as this function. The interval of convergence up here is going to be negative 1 less than x less than 1. Again, we did this earlier. That's how we were able to know what that series was on that one. If you want to see it, right there, written in a different format. And that is called term-by-term integration. Again, you will probably be told to do term-by-term differentiation or term-by-term integration. Otherwise, it just takes like a lot of know-how to figure that out. And last but certainly not least, there's the assignment. Check next time to find it. Oh, smash that like button right down there.